Alright, now we're moving on to question number 9, and this is a question about a semicircular ring of charge, and we're given the total charge of the ring is 7.3 microcoulombs, and the radius of the ring is equal to 0.55 meters. So this is positive 7.3, so it's a positive charge on this ring. The question is asking for what is the magnitude of the electric field in newtons per coulomb at point P in the center of the semicircle. So this is a semicircle as well, which is useful because that gives us a lot of symmetry to work with. And specifically the symmetry I'm talking about is that if you notice, so we draw the electric field lines caused by each of these small areas inside of this charge segment. You see that from the top segment we have well, it should be directly straight down because it's asking for the center of the semicircle. It looks like this, but in the exact opposite side, we also have an exactly counteracting one. And basically what that counteracting one does is it cancels out the y components, right? You see that this works for every single point. If we choose a point right here, for example, then that means that there's always going to be another point on the other side where its y component exactly cancels out this y component. So what we are really concerned with when we're trying to integrate over the semicircle is the force and the electric field in the x direction, right? So let me just erase all this stuff. All right. So let's try to figure out what's the formula for dE first. So for every small charge segment, specifically not just the entire magnitude of this dE, but actually we care about the x component, right? So let's start, like, say from this dE, okay? This is the dE where we want to find, and it has a charge dQ associated with it, right? So this is equal to k dQ over r squared. Now, if you remember from the previous video, the strategy we used is to use density, right? Because the density of this entire thing is constant no matter how small of a charge you want to look at, or how small of an area you want to look at. So the density is always going to be Q over the length, and that's equal to the density, right? And length in this case is just 2 pi times r divided by 2, right? Because it's just a semicircle, it's just as pi r. So now let's look at what the dq would be, right? So dq over the specific length that the dq passes over, so I'm going to call it dl, is equal to the density, same density as this, right? Now, instead of calling this DL, though, there's an easier way we could do it. So we could call it, if you remember, what is the, if this is a length L that we're concerned about, that the DQ is in, then what is the length of that arc, right? It's actually, if you remember some geometry stuff, it's actually just r times d theta. If this is, the angle in here is d theta. So this is dq divided by r d theta, and that's equal to the density still. So I'm gonna call this capital R actually. And you notice that the R is the same throughout this entire integration. So R is actually not dependent on anything else. It's not dependent on theta, it's just a constant. So if we plug this in to this equation, let's just bring it down. So dE x is equal to k, and then dq, so I'm going to plug in dq is equal to r rho d theta, and d rho is just the entire charge divided by 2 pi r over 2, so that's just pi r. So actually I can cancel out the 2 r's here. So actually I could write this as dq is equal to q over pi times d theta. So I'm gonna write that here, q over pi, and then d theta. But I can just bring out so this is divided by r squared, but r is actually constant, remember, throughout the integration. But there's the additional thing we must add, right? Because this is in the x component, right? So we actually can't just take only because right now what we have this equation, it's calculating the entire magnitude of the electric field at this point. But see, we only want this electric field right here though, right? We don't want to consider the y component. So if we could define theta to be the angle from this top, actually I think it'll be easier to define theta as the angle from here actually. Theta is the angle from the center to the top, or this, yeah, center to the top, so this will be like positive pi over 2, and this will be negative pi over 2 down here. So then that means that this theta is also this theta, right, because of the opposite angles. And that way we can see that if we just use cosine of theta, then that will give us the x component of the electric field. So this should be cosine theta right here. So we had to add another cosine theta right here. And what we could do is we could actually just, let's just calculate, so let's actually now take the integral. It's asking us for the integral. Yeah, it's asking us for the integral. So if you take the integral of both sides, now we have, we can take out the r squared actually, so I'm just going to take the r squared out here, because again, it's constant, so we don't even worry about it. So it's just we're just integrating cosine theta, okay, and so this obviously just becomes the entire electric field. So go to kq over pi r squared times cosine theta d theta. Now, just in case if there's like something weird going on, what we could actually do is just look at the electric field of half of the semicircle, so just from here to here. Actually, you know what? I'll just do the entire semicircle. So the way that we define theta is that theta is 0 here at the midpoint, and that theta right here is going to be negative pi over 2, and then theta here is going to be pi over 2, right? So that means that this is going from negative pi over 2 to pi over 2. Okay. And in the end, if we get a negative number, we know to just make it a positive number because we just define the positive axis where we want. So what is the integral of cosine theta? Well, it's just sine theta, right? So sine theta, and that's going from pi over 2 to negative pi over 2. So what is sine of pi over 2? That's 1, right? So that's just going to be 1. And then minus sine of negative pi over 2, that's negative 1, right? So minus a negative 1 is 1 plus 1, right? So that's just 2. So basically our electric field is equal to kq over pi r squared times 2. So this is the equation. Let me just check if I got this correct or not. So yeah, I just checked my answer, and this is correct. The only thing is that you just got to plug in your numbers because it doesn't want the equation, it just wants you to plug in the numbers. I won't plug in the numbers in this video because your numbers are probably different than my numbers though. Alright, good luck.